Now here's a quick recap of all the tests that we've studied thus far in this chapter to allow us to determine if a series converges or diverges. The first thing we have is our known series. So we have geometric series, and we know that those always look like this. The sum from n equals 0 to infinity of a times r to the n. There, if the absolute value of r is greater than or equal to 1, you diverge. And if the absolute value of r is less than 1, you converge. P series and P series were in the form the sum from n equal 1 to infinity of 1 over n to the p. So for a P series, if P was less than or equal to 1, you diverge, and if P was greater than 1, you converge. For a telescoping series, we always had that minus sign. And what we did with a telescoping series is found the sequence of partial sums. Once we found that sequence of partial sums, S sub n, we took the limit as n goes to infinity of that sequence. If the limit existed, the series converges. If the limit did not exist, the series diverged. After our known series, we looked at 7 different tests. The first one, the nth term test. The nth term test said to take the limit as n goes to infinity of a sub n. If you don't get 0, then your series diverges. If you do get 0, the test is inconclusive. You have to find a different test. The integral test. Now with the integral test, we had to show that our function was positive, continuous, and decreasing for x's greater than or equal to 1. And once we showed that, then we could say that our infinite series was equal to the improper integral, and then we evaluated the improper integral. If the integral converged, so did our series, and if the integral diverged, so did our series. Then we talked about the direct comparison test. For the direct comparison test, we had to find something to compare our series to. Once we found what we compared our series to, if that comparison converged, it had to be the larger series. If that comparison diverged, it had to be the smaller series. The limit comparison test also had us determining what we would want to compare our series to. And once we did that, we had to take the limit as n goes to infinity of our given divided by what we're comparing it to, our known series. And if we ended up with L, where L was a finite positive number, then whatever our known series did, our series does. So they either both converge or both diverge. The ratio and the root test we just looked at in this section. For the ratio test, we know that we converge absolutely if the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n is less than 1. We diverge if that limit is greater than 1 or equal to infinity. And if it's equal to 1, our test is inconclusive. We have to use a different test. The root test said we converged absolutely if the limit as n goes to infinity of the nth root of the absolute value of a sub n was less than 1. We diverge if that limit is greater than 1 or if that limit is equal to infinity. And the test was inconclusive. If that limit was equal to 1, we'd have to choose a different test in order to determine if our series converged or diverged. The last thing we looked at was the alternating series test. Now, an alternating series test can only be done on a series that alternates. So once we take the absolute value, so we have a sub n greater than 0, we said that our alternating series converges if the limit as n goes to infinity of a sub n was equal to 0, and a sub n plus 1 was less than or equal to a sub n for all n, so it was decreasing. Recall for us, we only tried the alternating series test after we showed that the absolute value of our series diverged, and this gave us conditional convergence. Let's do the last 3 examples where we're asked to determine the convergence or divergence of the series using any appropriate test from this chapter. Identify the test used. So for the next 3 examples, we can use any of the 7 tests that we looked at, or if it's a known series, one of those 3 known series. Number 6 is the sum from n equal 1 to infinity of 10 divided by 3 times the square root of n cubed. Well, notice that 10 and 3 are just multiplying. Those are then constant multipliers. If you're a constant multiplier, you can be factored out of the series. So this becomes 10/3 times the sum from n equal 1 to infinity of 1 over, and then instead of writing it as the square root of n cubed, we can write this as n to the 3/2 power. We need to determine, does this series converge or diverge? Well, this is a known series. It's a p series. Your p here is equal to 3/2, and that's a number that's greater than 1, therefore you know that this series converges. What about example 7, the sum from n equal 1 to infinity of e to the negative n times n factorial? Well, the first thing is to get rid of the negative exponent. So let's rewrite it without a negative exponent and then determine which test to use. So we're looking at the sum from n equal 1 to infinity of n factorial over e to the n. Now this is not a known series, and what we said in the last few sections was the next thing you tried was the nth term test. Well, I'm not going to do an nth term test with this because of the factorial. When your series has a factorial, you should always start by trying the ratio test. Therefore, we're going to try the ratio test on this because of our factorial. So we do the limit as n goes to infinity of the absolute value of a sub n plus 1. Well, if this is my a sub n, then a sub n plus 1 is going to be n plus 1 factorial divided by e to the n plus 1. And then I need to multiply by the reciprocal of a sub n. Multiplying by the reciprocal of this, I have e to the n over n factorial. Now I have to simplify this. So I'm looking at the limit as n goes to infinity of the absolute value. Well, this is a factorial and this is a factorial. Which one is larger? This one right here. Let's expand that. So that'll be n plus 1 times n factorial. And I'm going to put it all over n factorial. Then times e to the n. And if I expand e to the n plus 1, I know that's e to the n times e to the first. Now notice that your n factorials cancel, and so do your e to the n's. That leaves you with the limit as n goes to infinity of the absolute value of n plus 1 all over e. Well, what's the limit as n goes to infinity of n plus 1 over e? Well, that's going to be infinity divided by e, the number, and infinity divided by a number is equal to infinity. Since we got infinity, we know that therefore by the ratio test, our series diverges. Our last one, number 8, the sum from n equal 2 to infinity of negative 1 to the n divided by n times the natural log of n. First, I notice that this is an alternating series. Since it's an alternating series, the first thing I need to do is take the absolute value of a sub n. Well, the absolute value of a sub n is going to equal 1 over n natural log of n, because when you take the absolute value of negative 1 to the n, all you have left is 1. Now I have to determine if that converges or diverges. Well, it's not a known series. If we were to try the nth term test, we'd get 1 over infinity, which is 0. That test would fail, so I have to find a different test to use. When I have the natural log, I'm either going to try to compare it to a divergent p series, like a 1 over n, or if I can, I try the integral test. Since this is something that you can integrate, we're going to use the integral test because that's going to be the easiest way to determine if it converges or diverges. If I rewrite this as a function, I know this is f of x is equal to 1 over x times the natural log of x. The first thing I need to do is show that this is continuous, positive, and decreasing so that I can use the integral test. To determine continuity, we would have to find domain. Set the denominator equal to 0 and solve for x. So this is x is equal to 0, and then the natural log of x is equal to 0. This is solved for x, so we're all done. Here, if I make e the base, e to the natural log of x is equal to e to the 0. These cancel, and I get x is equal to 1. So I know that I can't be 1, and I can't be 0, but I also have the natural log here. And remember, when you have the natural log, you have to set the argument of the natural log greater than 0 and solve for x. Well, that's already solved for x, so I know that my domain is going to be a combination of all of these. It's going to be x's such that x has to be greater than 0, x can't equal 0. Well, I already have that it can't equal 0 because there's not an equal to sign there. And then x cannot equal 1. Well, where am I starting? I'm starting at the counter of 2. Because it's not part of the domain, we can therefore say that we are continuous for x's greater than or equal to 2. Now let's determine if it's positive. Well, we had that f of x is equal to 1 over x natural log of x. Well, the numerator is always positive, and the denominator for both x and the natural log of x is going to be positive for x is greater than or equal to 2. Therefore, we know that this is positive for x is greater than or equal to 2 because a positive divided by a positive is equal to a positive. Finally, we had to figure out if we were decreasing. How did we do that? We found the derivative. If this is my function, the derivative using the quotient rule would be denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, but be careful because that's a product. Call that our first term, and we'll call this our second term. So we'll say it's going to be the first times the derivative of the second. Well, the derivative of the natural log of x is 1 over x plus the second, which is just the natural log of x, times the derivative of the first. Well, the derivative of x is 1, and I don't need to write that, so I just end up with x times 1 over x plus the natural log of x. And this is all over the denominator squared, which is x natural log of x squared. Well, here I'm multiplying something by 0, so I know that cancels. And here I have x times a 1 over x, so I also know the x's cancel. Therefore, this derivative, f prime of x, is going to equal negative. And then inside the parentheses, it's a 1 plus the natural log of x. And this is all over x natural log of x squared. Now, the denominator is always positive because we're squaring it. And the numerator, well, remember, for x is greater than or equal to 2, the natural log of x is positive. So a positive plus 1 is still positive, but times a negative is going to be negative. So that's going to be negative for your x's greater than or equal to 2. And a negative divided by a positive is going to equal a negative. And since it's equal to a negative, we can say that we are decreasing for x's greater than or equal to 2. What does that mean? That means that the integral test applies. So for the integral test, remember, you have to show that you are continuous, that you are positive, and that you are decreasing, in this case, for x's greater than or equal to 2. Now let's perform the integral test. So we set our series, the sum from n equal 2 to infinity of 1 over n times the natural log of n equal to the improper integral, and the improper integral is the integral from 2 to infinity of 1 over x times the natural log of x dx. Can I integrate this? Yes, it would require a u sub. We need to let u equal the natural log of x. If u is equal to the natural log of x, the derivative du would be 1 over x dx, which is perfect because all I have is a 1 over x dx. Rewriting the improper integral as a limit statement, the limit as c goes to infinity of the integral from x equal 2 to x equals c, and then this becomes a 1 over u du. That is something that I can integrate. The integral of 1 over u du is the natural log of the absolute value of u, and this gets evaluated from x equal 2 to x equals c. Get out of u's and go back into x's, and we're looking at the limit as c goes to infinity of the natural log of the absolute value of the natural log of x, evaluated from 2 to c. Plug in those limits of integration. The limit as c goes to infinity of the natural log of c minus the natural log of the natural log of 2. Well, this guy here, the natural log of the natural log of 2 is just a number. So when you take the limit as c goes to infinity of a constant, it's just going to be that constant. Here, the natural log of c when c goes to infinity is infinity, and then the natural log of infinity is also infinity, so we have infinity minus a number. Well, infinity minus a number is equal to infinity, and since we got infinity, we knew that therefore our integral diverges. And if our integral diverges, Therefore, by the integral test, our series diverges. Well, we're not done because remember, we just took the absolute value of a sub n in order to do this. This was an alternating series. Now that we've shown that the absolute value diverges, now we had to try the alternating series test. The alternating series test had two conditions. Condition number one, the limit as n goes to infinity of a sub n. Well, remember that a sub n is this guy here, this 1 over n times the natural log of n. So the limit as n goes to infinity of 1 over n times the natural log of n had to be 0. Well, that is 0 because that's 1 over infinity. So the first condition for the alternating series test has been met. Condition number 2, a sub n plus 1 had to be less than or equal to a sub n for all n. Well, remember, all this meant was that you were decreasing. Well, didn't I already show that I was decreasing? Yes, I showed it over here, so that condition has been met. Since both conditions are met, we can therefore say that by the alternating series test, our series converges conditionally. That's it for the ratio and root test.